Hello, my name is Ian Oshab. I am a second year mechanical engineering student at the University of Florida. I am on the University of Florida's Formula student team, Gator Motorsports, and this is an adaptation of a lecture that I recently gave to some of the younger members of Gator Motorsports. This is an introduction to springs and dampers, and especially this is going to be how they apply to a Formula student car, but certainly you could adapt this information to any type of vehicle that uses springs and dampers. So real quick, let's talk about some motivations as to why we want to understand our springs and dampers. Firstly, we want to be able to normalize a car for future testing, to be able to compare to how the car feels now, to past, to future, and be able to actually compare apples to apples if other things are changing to the car. We also want to be able to understand and quantify our setup changes and predict how the car is going to respond when we actually get out there and drive it. If you can give it a number to a change that you're making to the car, you can actually get a really good idea of how much of a difference it's actually going to make, and if the driver is going to be able to notice it, or if you'll be able to notice it in your test data. Another thing for teams that have access to a lap sim software is if you can understand how the springs and dampers are going to work during the design phase, and you can design them to be pretty close to an ideal setup before you even get into the lap sim software, you're going to have a lot better time and you're going to get a lot better results out of it. But I think the biggest reason that you want to understand them is to keep the tires happy. The tires are the only thing between you and the road. And if you can minimize the amount of load variations that are happening to the tires, you're going to get the most amount of grip, and the car is going to be the most controllable and predictable for the driver. So throughout this lecture, we're going to be talking about our simplified quarter car model. We're going to pretend like the car is 4 different masses on 4 different springs and dampers. You can see over here on the left that we have where is it? That we have our coordinate system. We're just talking about one dimension up and down. And we're going to say that as the mass of the car moves down, that's going to be positive displacement. Springs are going to be denoted with a spring stiffness K, and dampers are going to be denoted with a damping coefficient of C. And you can do the sum of your forces to get the mass times the acceleration. Our forces are going to be the force of the spring, the force of the damper, and gravity, which is going to be effectively constant. Now, going back to first principles real quick, the amount of force that you get from a spring is going to be directly proportional to the displacement, and it's going to be the displacement times the spring rate. So you see that the spring rate here is just going to be the slope of this graph, and for a given displacement, you can very easily calculate the amount of force, or you can go the other way. For a given force, you can very easily calculate the amount of displacement that you're going to get. You can elect to put different spring rates on your car, front and back, for each corner, whatever you want. And usually they come in about 50-pound increments for our purposes in Formula Student. You can see graphs are a couple different spring rates. These are pretty common spring rates that you might want to run on a Formula Student car. Obviously there's a big range and you can figure out exactly what you want. But for the same displacement, you get different amounts of force, or you can also think of it as for the same amount of force, you get different displacements. And as you can see, I've only plotted positive displacements because in general, we're going to be talking about compression springs, not ones that work in tension. Now, you can also do this thing to a spring called preload. You pre-compress it before you put it on the car so that there's already some built-up tension, and you can see the orange is representative of a 350-pound spring that has had some preload added to it. So the whole graph is going to shift to the left a little bit, and you see that for any given displacement, you're going to have more amount of force coming from the spring because you've already added some tension to it, and you're just going to stack on top of that. So in order to get the spring to move at all, you have to overcome that amount of preload, and the maximum amount of force that you can get is going to be greater than the maximum amount of force of the same spring with no preload. Now, it's usually a pretty good idea to have some amount of preload just to prevent your suspension system from rattling loose as you're driving around, but it is definitely possible to have too much preload. You can also look and see that when you put the weight of the car on the spring, let's say that our corner is going to weigh 100 pounds, you are going to displace some amount And you can actually figure out what that amount is by just measuring the spring, or you can calculate it. And you can see that for the orange spring, or yeah, for the orange spring, we'll displace, about 0.08 inches, for the blue one, 0.18, and for the red one, about 0.28. You can express the amount that you displace when you put the weight of the car on the ground as a percentage of your total travel, right? We'll say that we have 1 inch of travel for this example. If we displace 0.08 inches and we have a total travel of 1 inch, then we are going to get a sag, right? The sag is going to be how much it compresses when we put the weight of the car on the ground. It's going to sag 8% or 18% or 28%. And I didn't purposely make the numbers work out like that. They just kind of did. But anyway, how do you know what amount of sag and what amount of preload and what amount of or what spring rate you want? Well, the best way is to look at your data from your test sessions. Over here on the left, you can see that this is an example of too much preload. We're sitting too high in our travel, right? These gray bars are going to represent the ends of our travel, where this lower gray bar is the shock is fully extended, versus this upper gray bar is going to be the shock is fully compressed, and we can't go any more than that. And you can see that with too much preload, we're regularly going to be having the shock fully extended. And that's obviously not ideal, because if the shock is fully extended, the wheel, it takes very little change in the profile of the road for the wheel to actually come up in the air and lose grip. And then obviously, if one of your wheels is in the air, you're not going to be able to turn as hard. So you want to avoid that. Over here, you can see an example of not having enough preload. You can see that regularly we are bottoming out the shock, where we're getting to the ends of our travel and we're hitting the bump stops. And this is bad because it can put a lot of shock through the suspension system, and it can put a lot of shock on the tire, and you can suddenly lose grip very easily, which is not that great. Now, this one over here, this is a spring that's too soft. We're not sitting too high or too low in our travel. We're just using way too much of it. We need to choose a stiffer spring to rein this graph in here and squish it down a little bit so that we aren't hitting the ends of our travel. Ideally, you get pretty close to the ends of your travel so that you're not just like designing a bunch of extra suspension travel into your system that you don't need. But you don't actually want to hit the ends, and you don't want to have way too much travel that you're not actually going to be using. But this kind of analysis isn't the end all be all. Now, obviously, when you're designing the suspension system, you probably won't have access to data kind of like this. So you need to have some kind of way to choose your spring rates before you actually get out there, proactively. But before we do that, I just like to make a quick note about motion ratios. Motion ratios are really important, and sometimes I'll be talking about something in the rest of this lecture, and I'm just going to assume that you take the motion ratio into account. But the motion ratio essentially is just the amount that your wheel moves is not going to be the same amount that your spring moves, right? And we're interested in the effective spring rate at the wheel, because that's what's going to be acting on the mass of the body. But we put a specific spring on the car. And you can, for this example, see how we have a wheel, it's just on a solid axle, and it's going to pivot about point A, and we have a spring that's half the distance away. I chose half just to make the numbers easier. But the spring moves half the amount that the wheel is going to move. And so we can sum the moments about A and set those equal to 0, and say that the force of the spring is going to be equal to, or the force of the spring times its moment arm, d over 2, minus the force of the wheel times its moment arm, d, they're gonna be equal to 0 when we combine them. And so we can sub in Hooke's law, and we can say that the spring rate at the wheel times the displacement of the wheel is going to be equal to the spring rate of the spring times the displacement of the spring times 0.5. When I say the spring rate of the wheel, I'm not talking about like the spring rate of the tire. This is the spring rate that the wheel effectively sees as a result of the spring, the force from the spring going through this system and out to the contact patch, right? And so we have some variables here that we don't know. If we sub in from up above that the displacement of the spring is going to be half of the displacement of the wheel, we can solve and figure out that the effective spring rate at the wheel is going to be equal to 0.5 squared times the spring rate that you actually put on the car. And so this is really important. The effective spring rate at the wheel is going to be equal to the motion ratio squared times the spring rate that you put on there, right? The reason that it's squared, obviously we showed it mathematically, but an intuitive way to think about it is the wheel is going to be twice the distance away from A. So the force here is going to be doubled when it gets here, right? But this one moves half as much as this one does. So you get the effect in both directions, right? The force here has to be twice as big, but it also moves half as much. So you end up with the motion ratio squared. But when you're just talking about the force, right, it's not going to be the motion ratio squared. It's just the motion ratio times the spring rate times the displacement of the spring, which you can derive very easily from this equation right here. Now, into some normalizing, the ride frequency is a really important parameter that you can use to normalize the performance of your car. When you have a mass on a spring and you disturb it, it's going to oscillate at some natural frequency, and you can calculate that frequency using this equation. We'll go through a real quick example, but you can see over here on the right side, this is an example of just the displacement following a natural sinusoid as a function of time. So this is actually from the front left corner of the second test session for Gator Motorsports. Our corner weight was 125.9 pounds. This is the corner weight excluding the weight of like the uprights and the wheels and the brakes and stuff like that. This is just the mass of the body on that corner. Then our spring rate was 450 pounds. Our motion ratio was 0.81, which is a pretty typical number. And gravity, if you have never seen gravity measured in inches per second squared, this is probably pretty jarring, but gravity measured in inches per second squared is 386.09. The reason that I have gravity here is because our corner weight was measured in pound force, and you can see from this equation that we actually want it to be in units of mass. So we throw our spring rate in there, we throw in our motion ratio squared, right, to take care of that because we're worried about the effective spring rate at the wheel, and you put in your mass here, and you get a ride frequency of 4.79 hertz. So no matter how much you displace the mass, if there's no damping there, it's just going to oscillate at a frequency of 4.79 hertz. You can also convert this to radians per second just by multiplying by 2 pi, and you get 30.1 radians per second. So that'll be it for springs for right now. But the ride frequency is probably the most important way to characterize your spring choice, right, and how the car is going to behave. To give you a sense of scale, a typical like passenger car, right, like a normal passenger car, is going to have a ride frequency of about like 0.8-ish. A sporty two-door car that's like street legal is going to have a ride frequency maybe like 1.2 hertz. And you can see like a Formula Student car has a ride frequency of like 4 or 5 hertz. So these things are really, really stiffly sprung. They're really, really aggressive. And they're not very comfortable, but they're fast. So, and I guess a little bit more of a frame of reference, a Formula 3 car is going to be at like 7 or 8 hertz. So, they're even more crazy aggressive than a Formula Student car. There isn't a particular number that you're shooting for here, though. It's just, again, kind of a way to normalize and to be able to compare your car to previous and future setups. It's not like you have an equation where you can calculate what's the ideal frequency or anything like that. So let's talk about dampers real quick. This is a very simple hydraulic damper. You've got a cylinder here and you're going to fill it up with oil, and then you throw a piston on the inside and you can push the piston in and out, and you can get a force from there. You're going to have the head of the piston, but you'll drill some holes in it so that the oil can flow through those holes. But because it's oil, it's pretty viscous. It doesn't really want to flow through there. And you can imagine how if you push this very, very slowly, you're going to get very, very little force here because the oil can very easily go through here. But if you try and move this really, really fast, you're going to get a lot of resistance to the flow because the oil won't be able to get through these tiny little openings very quickly. So if you plot the amount of force that you get from the damper versus the velocity that you move it at, you'll actually get a line. And you can do it in both directions. You can compress it and you can extend it. Now, usually the amount of force that you get, the slope of the force versus velocity is going to be steeper for compression versus rebound, where compression is the mass moving down and rebound is the mass moving up. But either way, you get a line, and you can express this line as the force of the damper is going to be equal to x dot of the damper. This is just the velocity of the damper, but the dot is like a fancy way to write it. This is just saying the first derivative of the position, and the coefficient of, or the damping coefficient, right? Similar to the spring, you just have a coefficient times some number. For nicer shocks, like you'll usually see on a Formula Student car, you'll actually have two regions where there's a low speed and a high speed region. There's some type of blow off valve right around here that flattens out the slope for the high speed region so that you have a lower damping coefficient. And it'd be pretty hard to design a damper where the slope increases. You can certainly do it. I'm sure that exists. But usually you see that it flattens out here. So you'll have a low speed and a high speed region, and usually you'll have low speed and high speed for rebound as well. I just haven't drawn that on this graph here. So if you consider the whole spring and damper assembly, the total force that you're making there is just going to be equal to the spring rate times the displacement plus the damping coefficient times the velocity. And again, similar to spring rate, the coefficient at the wheel is going to be equal to the motion ratio squared times the damping coefficient of the damper. But the force at the wheel is just going to be the motion ratio not squared times the velocity of the damper and the coefficient of the damper, right? And you can do a real quick unit analysis. You can see that the units of the damping coefficient are going to be pounds per inch per second. So this is a schematic of the Öhlins TTX25 Mark II FSAE shocks. This is a pretty common shock for FSAE teams to use. This is what Gator Motorsports uses at the moment. And so I'm just going to real quick run through how the internals of this guy work. So you've got a reservoir here, right? You've got that cylinder full of oil. But the difference is that this piston over here doesn't have any holes drilled in it. So when it moves up, all of this oil that's in here only has one choice. It has to go through this through this valving here. And then it goes through and it gets to these guys. And there's lots of complicated stuff that happens here. There's three different things that are here. This is a check valve. The oil can't flow through this direction, but it can flow through from this direction. This is your low speed adjuster. You adjust it with an Allen key and you screw it in or out. And you can see how that adjusts how big this opening is here, how big of a space there is for the oil to get through. And then here you have another adjuster. This adjusts the preload on a spring here. So normally this is sealed shut, but you can imagine that if the pressure in the oil gets great enough, it'll be able to overcome this spring and push past, and you'll have a much bigger opening for the oil to get through. Over here you have the similar thing, but for rebound damping, and you have this same check valve where once the oil gets past this stuff, it doesn't have to deal with this adjuster or this adjuster. It just goes straight through and it goes back and it fills in the space behind the piston. You also have a reservoir here and some pressurized nitrogen to prevent the oil from cavitating with the high pressure differences and stuff like that. And just to give you some extra oil so that you have a little bit of a heat sink. Now, this one here, this is your low speed damper. This adjusts the low speed region. And this is a high speed damper. This adjusts what threshold the high speed region is going to start out at. And you've got the same for rebound as well. Now, let's look at a dyno plot. I know the numbers are really small, so I'm going to do my best to explain it. But essentially, what Öhlins does, this is a graph that comes straight from Öhlins. They turn the high speed adjusters on the dampers all the way in. They make them as tight as they can go, most amount of preload, and then they sweep and they try out different amounts of low speed damping, right? And you can see this is the most amount of low speed damping, and then they have less and less and less and less, and they go for different intervals, right? And so this is 0 clicks, 2 clicks, 4 clicks, 6 clicks, 10 clicks, 15, and 25. Now, you can see that the slope for the different amount of low speed clicks in the low speed region, that changes, right? But the high speed slope doesn't really change all that much, right? And there's a certain threshold where the high speed region starts, and that doesn't really change either. You can also see that there's the compression stroke, and there's also rebound down here. Technically, all of these graphs should be like in quadrant 3 of the graph over here, but Öhlins just gives this to you in absolute velocity. They also plot the coefficients, or they give you plots of different high speed settings. So here they make the low speed dampers as stiff as they can go. And then they try out different high-speed settings, so 4.3 turns, 3 turns, 2 turns, 1 turn, 0 turns. And you can see that the high-speed adjuster actually doesn't really change the slope of the high-speed region. It does a little bit for this one, right? It's a little bit of an outlier. All it really does is it changes the threshold at which this high-speed region is going to open up. But this leaves us with the big problem, because even though there's a lot of great information here, you can tabulate this, and you can kind of see how, like, you're missing information in between, 0 clicks and 2 clicks, right? What does the graph for 1 click look like? It's going to be somewhere in the middle here, but you don't know what it is. And then there's also information in between the different high speed settings, right? There's 4.3 turns and 3 turns, but what about 3.5 turns and 2.5 turns and 1.5 turns? And what about 1 click and 3.5 turns, right? There's all this information that's missing here. And ideally, we'd have a different graph for every single possible permutation and combination for compression and rebound, but that's just a lot of information. So what you end up having to do is you got to make a model, right? So you can tabulate, you can measure by hand with a ruler, or you can measure with your favorite software, the amount or the slope for different amounts of low speed clicks. And this is what I was able to come up with. You can do your own analysis and see if you get your own numbers. But this is what I came up with for the specific C11, R11 valves that we have in our dampers. And if you plot this, you'll get a graph that looks kind of like this, where the x-axis is the number of clicks, the y-axis is the damping coefficient. And you can see that you get some type of graph that looks like, I'm not sure if it's inverse exponential, but it looks kind of inverse exponential, like some type of decay kind of situation, right? Where it starts out very steep and then it kind of flattens out, right? And so ideally, we'd be able to just like interpolate, right, the what the slope would be for the first one, but you can't, because obviously it's very, very exponential decay like, right? I'm not saying it is exponential, it might not be, but it looks very inverse exponential. So if you remember from high school class, when your professor would have you plot different types of data to figure out, like, how is this proportional, right? What plot gets me a straight line? Well, if you end up plotting the number of low speed clicks versus 1 over the slope of the low speed region, you'll actually get a straight line, right? And this is what I was able to get. I was able to get an R squared, a coefficient of determination of 0.9987, so pretty dang straight line. And you can see how the slope of this line actually gives you 1 divided by your damping coefficient, where x is your number of clicks. So you can figure out what your damping coefficient for the low speed region is going to be as a function of just how many clicks you have. And then similarly, you can do that for rebound. Now, as I said, the slope of the high speed region, I assumed to just be constant, right? This is a model. It's not going to be perfectly accurate, but that's what I did. And I said the number of high speed turns is actually going to change the threshold at which your high speed region starts, right? The amount of force at which your high speed region starts, not the velocity. And if you plot that, you get a straight line. All lines are straight, but and you can figure out what the threshold is going to be as a function of how many turns of high speed compression you do and high speed rebound. So real quick, the problem that we had was that we don't have data for all of the damper settings or all the combinations. And so we need some kind of way to like interpolate data and figure out what it's going to be in the middle. And in order to do that, we had to linearize the data. So the logic for determining what your damping coefficient is going to be, because there's 4 possible things that it could be, right? And, depending on, or there's 4 different regions, right? Compression, low speed, compression, high speed, and then rebound. So your logic process is going to be, let's figure out if we're in rebound or compression, and then let's determine if let's assume that we're in the low speed region, right? Because we don't know where the threshold is yet. Let's assume that we're in the low speed region and figure out the slope of that. And depending on the low speed setting that we're on, we can figure out if we are going to be above the force threshold for the high speed region. And if we are above that threshold, then we can switch to the high speed line. And then you got a race car, right? And so now that we have a way to figure out what our damping coefficients are going to be, we can use that and we can calculate a damping ratio. The damping ratio is given the letter zeta. It's a Greek letter. And this is the formula to calculate the damping ratio. Here's a graph of a couple different damping ratios, and you can see how the amount of damping that you have changes what the car responds like. Where if you have a very low damping ratio, you're going to get quite a bit of oscillation before the car settles out. Versus if you have like way too much, right? Like you see, the damping coefficient is 1.63. The car takes forever to get back to its equilibrium position. And in theory, a damping coefficient of 1 is quote unquote critically damped, where the car returns to the equilibrium position as fast as possible without overshooting. But you can see that even a damping coefficient of 1 isn't really going to be like your ideal for a race car, because zero point 0.7, that's still right. Like it only overshoots by a little bit and it flattens out the quickest. So like, zero point 0.7 might actually be a little bit better, arguably, right? And so you can get different damping ratios depending on your low speed region and your high speed region. And these are going to apply to like different aspects about what you're trying to do with the car. 0.3 to 0.4 is going to filter out small road bumps. So like very small changes in the surface of the road. 0.5 to 1 is going to control large body movements like braking, accelerating, and turning. And then greater than 1 is going to do some extreme body control with like a very high downforce car, right? More downforce than a Formula student car is going to make, or driving temperature into the tires. So let's do a quick recap, summarize what we've learned so far. The natural frequency of our car is going to be determined by our spring rate, and the equation to calculate this is going to be either this for hertz or this for radians per second. Sag is going to be determined by your spring rate and your preload. I should have put an equation here. Let me actually just draw this out. I meant to include this, but I didn't. This is going to be like what is it going to be? It's going to be like can I draw? Yeah, XS divided by like X total, right? Where XS is like the amount that it displaces when you put the weight of the car, and X total is going to be the total amount of travel that you have. And then your damping ratio is going to apply to your dampers and the damper settings, and it's going to be given by this equation right here. So some suggested resources, if you're looking to learn more about this kind of stuff and you want to read more, I would first suggest you to go to Tune to Win by Carol Smith, especially chapter 6. The whole of Tune to Win is a really great like introduction to vehicle dynamics if you really don't know anything about it. But you'll quickly kind of realize that it has its limitations. Next, you can go to Race Car Vehicle Dynamics by Millikan. I think chapter 18 for learning about load transfer is great, and chapter 22 for learning about dampers is pretty good. It is a little bit textbook-like. Actually, it is really textbooks-like. It's like 800 pages long, so it's a tough read. But if you have a friend who knows quite a bit about vehicle dynamics, you can try and read Race Car Vehicle Dynamics and then ask them about it. And then I think personally that The Dynamics of the Race Car, written by Danny Nolan, is the best vehicle dynamics book that I have ever written, or I have ever read that I've ever read. So if you want to read chapter 4 from that, that's got a lot of really, really great information in it. And we're going to talk a little bit more about some of the information that you can get out of there. But this has been kind of like the introductory stuff. And in a second, we're going to get into more complicated stuff, because you're going to see that our simplified quarter car model, it's great, it's quick and dirty, but it isn't the whole picture, right? So, okay, so now that we've learned about the simplified quarter car model, let's look at a more complicated model. Now, when we want to do our simplified quarter car model, we exclude the fact that the tire is going to have its own spring rate, and we're also going to exclude the fact that the wheels and the brakes and the uprights, those are all going to have their own mass. But let's consider them now. Let's say that we have the mass of our wheel and the spring rate of the tire and the position of the wheel, in addition to the mass of the body and the spring rate of the body, or the spring that supports the body and the damper that supports the body and the position of the body, right? And so the math here is going to get kind of complicated. If you've taken like a linear algebra class, or maybe like some kind of numerical methods class, that would probably help you out a lot here. But we're going to be dealing with vectors and matrices. So it's not complicated, but it does look pretty intimidating. And if you want, you can kind of skip ahead or just bear with me for the math, but hopefully it'll make sense by the end. So what we're going to stick to is we're going to say that the sum of the forces equals MA, right, on each body. And we can write an x vector, and we can make this vector anything we want. But for state space modeling, what we're going to do is we are going to make this vector the velocity of the body, the position of the body, the velocity of the wheel, and the position of the wheel. But in order to make our analysis easier, what we would like to do is we would actually like to not have any derivatives in here. So we decide to call the velocity of the body x1 and the position of the body x2, and we do x3 and x4, just so that we're not dealing with derivatives. All right, we're allowed to do this. Then what we can do is we can use our F equals ma and say that the mass of the body times the acceleration of the body, where x1 is equal to xb dot, so x1 dot is xb double dot, the acceleration of the body. The mass times the acceleration of the body is going to be equal to the force from the spring and the force from the damper. You also get something similar right here, where the mass of the wheel times the acceleration of the wheel is going to be equal to the force from the body spring, the force from the body damper, and then also the force from the tire spring, right? Now here we have x2 dot, right? Really what we're doing is we're trying to find the derivative of this vector right here, right? So we figure out what is x2 dot. Well, x2 is equal to xb, so x2 dot is equal to xb dot. Well, xb dot is equal to x1. So x2 dot is equal to x1, and then x4 dot, similar thing over here, x4 dot is equal to x3. Now, if we divide this equation and this equation by the mass, we get that the derivative of x is going to be equal to a bunch of coefficients times our original x vector. And we can write that in matrix form. The derivative of x is going to be equal to a matrix of a bunch of coefficients times our original x vector, right? Or a times x. And this is a first order linear differential equation. You can see all of these different terms in this matrix. These are just numbers. There's no there's no variables in here. There's nothing in here that changes. So it's just a bunch of numbers, right? Now we can take this and we can find the eigenvalues of this matrix. And eigenvalues will have the form of a real component plus minus an imaginary component, where this I here is the imaginary number, the square root of -1. This I here denotes that you're going to have multiple eigenvalues. This is a 4x4 matrix, so you're going to have 4 different eigenvalues. When you calculate your eigenvalues, which the process of calculating the eigenvalues isn't as important here, we are really just worried about the fact that you can do this. Society has figured this out. Humans have figured this out. You can also get your eigenvectors, which tell you some interesting stuff, but we are just going to be worrying about the eigenvalues for today. You can get some interesting stuff. You can get the natural frequency and the damping ratio of this whole system for each different eigenvalue, right? You have 4 different eigenvalues, so you'll get 4 different natural frequencies and 4 different damping ratios. Now, some of these are going to be like conjugate pairs, right? Where you'll have like a plus and a minus term. So you'll actually get the same natural frequency and the same damping ratio twice. But you can see how the parts of the eigenvalues you can plug into these equations and you'll get your natural frequency and your damping ratio. One thing I would like to point out is that you can see if you don't have this imaginary component of your eigenvalue, then your damping ratio is just going to be equal to 1. And that means that you're not going to have any oscillations. You're just going to have exponential decay. Okay, so let's look at an example. The car that we're going to be analyzing is the same one from the example that I used for the natural frequency from like way back when we were just talking about the simplified quarter car model, and we'll do low speed damping and high speed damping. So I have gone in and I've calculated, and you can see down here at the bottom, our simplified quarter car model predicted a natural frequency of 30.1 and a damping ratio of 0.974. Our high-speed region simplified quarter car model predicted, again, 30.1 and 0.199 damping ratio. Because we have multiple eigenvalues, though, there's actually multiple things happening at the same time. You're going to have this term, which, because there's no damping ratio, this is exponential decay. And this exponential decay is going to happen very quickly because it's a real big number, right? This is going to be a frequency, some oscillations where you have 38 radians per second that is going to be damped at a damping ratio of 0.34. And again, you have it twice because you have a conjugate pair. You have a plus I and a minus I. And then you'll have another slower than this one exponential decay. So really what you're going to notice is that this is going to be your oscillations that's going to be happening when you displace the car. And so we can compare that to the simplified quarter car model, and you can say that the natural frequency that we're going to actually see is going to be 38, where we predicted 30.1, and our damping ratio is actually going to be 0.34 versus we predicted 0.974. So you can see not a super great approximation here, but it is pretty good, right? Like we're only like 8 radians per second off for the natural frequency, and our damping ratio isn't that great. Now, over here, we have our high-speed damping, and we have, again, 30.1 and 0.199. And you can see that we actually have here 2 different frequencies that are going to be happening at the same time. We have 25.4 and 147.7. Again, we have 2 for each because we have a plus and a minus. These are going to have damping ratios of 0.114 and 0.314. So you can see that actually our damping ratio guesstimate was actually not that far off over here, but our natural frequency was really off of this higher one, but it was pretty not too bad for this lower one, right? So just a great way to compare, right? Our simplified quarter car model, these numbers can be calculated super easily in Excel, right? This is just a formula. But all of these eigenvalues and these formulas and stuff, this is really something that you need like MATLAB or whatever way you like to use Python, right? You need some kind of like more complicated model. So realistically, this stuff can be included in your setup sheet, and it can get you a pretty good idea of how the car is going to be. This stuff is like more so before the fact, after the fact, when you have some extra time to analyze, because this is a lot of information to process, right? But in general, I'd like to point you to one really big important thing. These ones that don't have a damping ratio, it's because there is no imaginary component of the eigenvalue. The fact that there's no imaginary component, the fact that there's no imaginary component means that there's no oscillations, right? So if you can minimize the amount of eigenvalues that have an imaginary component, you're going to have a very well damped car because you're not going to have any oscillations. The car's just going to hit the bumps and it's going to keep moving. So in general, when you are looking at your eigenvalues, your goal here is to choose a setup where you have very few eigenvalues with imaginary components. And you want the imaginary components of those eigenvalues to be as small as possible, right? So you can see over here, this is not a super great setup because the eigenvalues are mostly, right, especially for these ones, this is mostly imaginary, versus this one is a little bit less imaginary, but all of these have imaginary components. So you're going to have 2 frequencies happening at the same time. And obviously that's not very ideal, right? And you can see like even our simplified quarter car model predicted that, right? The damping here is really, really not that great. So again, to reiterate, you want to minimize the amount of imaginary terms that are in your eigenvalues in order to get closer to a car that feels quote unquote critically damped. Comparing different models to analyze the car, you have a range of complexity where on the low end, you have your simplified quarter car model. And as you move up, you get to more complicated models. And as you get more complicated, you get much more accurate. And then that kind of tapers off, right? And so I would say that our simplified quarter car is probably around like 1 or 1.5 on this like complexity scale where like we get pretty decent accuracy. But if you go a little bit more, right, to the state space quarter car, you can get a lot more accurate and you get to get a much better look at how the car is going to behave. The state space quarter car, though, isn't even like the most accurate way to do it, right? You can consider the fact that all of the corners of the car are going to be connected. And you can also consider the fact that like the wheels aren't going to move straight up and down, right? They're going to rotate about an instant center, and your motion ratio might change a little bit, and all that kind of stuff, right? But you know, it's a good idea. The more complicated, the harder it is to read, right? If you have a model that's like really, really complicated, it's going to take you a long time to parse through all the information. It's going to take you a long time to write it. It's going to take a long time for the computer to calculate it. So you have a trade-off versus like how accurate you want your model to be versus how readable and how easy to understand you want it to be. You can see how like this is still relatively simple in terms of like modeling a race car, right? The car isn't actually one mass on four corners with different masses, right? It's all connected. So you know, it does get much worse, but this already kind of stinks. I don't really want to look at all this stuff. So keep that in mind. The simplified quarter car model does have a time and a place. It's great to throw in a setup sheet, because it gives you a good idea what you're doing. But understand that it's not the full picture. Understand that the state space model for the quarter car isn't the whole picture. Understand that you'll never get the whole picture by doing math. But again, you can get pretty close if you get real savvy with your math. So that's the end of this lecture. Hopefully you enjoyed. If you have any questions, I suppose feel free to reach out to me by email. Again, I highly recommend reading those 3 books: Tuned to Win by Carroll Smith, Race Car Vehicle Dynamics. Don't read the whole thing, but read some of it, and The Dynamics of the Race Car by Danny Nolan. All great books, all super instrumental to my learning. And also don't forget to go smell the roses. Go enjoy your race car. You guys built a race car, assuming that you're on a Formula student team. Go build a race car. Go enjoy it. You can get trapped in the weeds a lot, but it's important to just understand that race car goes zoom. So again, hopefully you enjoyed, and have a good one. Bye-bye.